Hi, welcome to the live session 2 of the Points of Topology and Real course. My name is Shavik and I'm working in University Counseling Management Madras. Before starting, can anyone please confirm whether am I audible properly and is the screen visible to you, everybody?
Audible.
Okay. And is the screen visible to you, Mr. Mustaq?
Yes.
Okay, thank you, Mr. Okay, before starting, okay, so today we shall start by solving problems the matrix spaces itself. Okay, so before starting, let me know, do you have any doubt or any questions from previous session or any doubt, any questions from search session, anything else you want to ask, you can ask. I mean, because I mean this session is mostly for problem solving. So if you have any doubt, you can ask without hesitation. Or else, if you don't have any doubt, we can proceed for problem solving itself. I shall wait for a few minutes. First, let me know, do you have any doubt or any questions? Let me know if you have any question or doubt. Okay, it seems that you don't have any doubt. So, if you have any doubt, you can at any point of time you can stop me and ask. Okay. Okay. So today we can start by solving problems. Okay. Of matrix space itself. I mean, directly we can go topology, but from first for this session, for the upcoming session, we stick around the matrix space. Then we go to topology gradually. Okay, so that is the thing. So okay, okay, so here is the first question. 1 minute. Is it visible properly? Okay, 1 minute. Okay. First question is that find all open sets in discrete matrix space. So this is the first question. Find all open sets in discrete matrix space. So just for sake of recall, so the discrete matrix space on a space X, suppose D is a discrete, it is defined as follows. D of x comma y is equal to 0 if x equal to y and 1 otherwise. So this is a discrete metric. Now, using definition, try to find all possible discrete set of matrix space. Okay, okay. So I can give one possible hint, namely, um, hint is that Okay. So one possible hint is first try to show that singletons are open in discrete metric space. First it is try to show that singletons are open in discrete metric space. Please think about it and let me know if you are done with that. First try to show that singletons are open in discrete metric space. You can only use the definite discrete metric, that will be sufficient for this. Please think about it. Okay. Okay. So let me do it for you. Okay. So how to do this? So firstly, observe that. So consider the ball of radius half around x. So this consists of all y belongs to x such that d of xy is less than half. Okay. But if you look at the definition of the discrete metric space, then d of xi, this thing either can be 0 or can be 1. But d of xy less than half, this implies what? This implies d of xy has to be equal to 0. So this implies what? This contains all those y belongs to x such that d of xy is equal to 0. And by property of a metric, what we can say? We can say that this implies this equal to only singleton x. So this tells what? This tells that the singleton set x is nothing but the ball of radius half around x. So this tells that singleton x is open in x comma d, where d is a discrete metric space. D is discrete space. Okay. So this is the thing. So this tells what? This tells that in discrete metric space, singletons are already always open. Okay. So now singletons are always open. Now choose any subset A subset of X, any subset. Okay. So now this A can be written as union of singleton A belongs to A. It can be written in obviously. Okay. Now what we have just we have seen that each singletons are open in discrete metric space. Okay. So this tells what? Each singletons are open, and we already know the arbitrary union of open set is open. So this tells that what? This tells that this whole union, this arbitrary union, is also open in X. So, but observe that we chose a subset of X to be arbitrary, any subset. So this implies what? This implies any subset of X is open in In where? In discrete metric. So this tells what? Any subset of capital X always open in discrete metric. So in discrete metric, any subset is open set. Do you understand? Kindly please let me know. Do you understand this argument or not? If you have any doubt, you can stop and ask me. I shall wait for a few minutes. Please let me know.
Can
Do you
you
understand?
repeat? Can you
Sure.
repeat?
Sure. Okay. So 1 minute. Okay. So hmm. So firstly observe that in discrete. So firstly observe 1 minute, please. 1 minute. Okay. So firstly observe that in discrete metric space, singletons are open sets. Okay. So how to do that? So, so in this, so by definition of discrete matrix, any distance between any two points are 0 and 1. Okay. Now choose any open ball of radius half around X. This ball of radius half around X contains all those Y such that distance between X and Y is less than half. Correct. But from the definition of discrete metric, d of x comma y can either be 0 or can either be 1. But since the distance is less than half, so so open ball of radius half contains only those y such that d of xy is equal to 0. Then by property of metric d of xy equal to 0, then when it is possible, only it is possible y equal to x. So this tells that singleton x is nothing but the open ball of radius half around x. Okay. So this itself tells the singleton x open in a discrete metric space. Okay. So till now, do you understand? There is singletons are open in a
Yes,
discrete
sir.
metric space.
Yes, yes.
Now, okay. Now we choose any subset A of x. Okay. Now that subset can be obviously written as arbitrary union of the singletons of that from that set itself. Correct? Now each singleton is open, so the arbitrary union is also open. So this tells, and since capital A is any subset of capital X, so this tells that any subset of capital X is also open in discrete metric. So this solves the problem. Do you understand?
Yes.
Okay. What about others? Does everybody understand this problem? If not, please let me know. I should wait for a few minutes, or else we shall move for the next problem. If you have doubt, please ask me. Okay. So it seems this everyone understands problem. So we can now move to the next problem. So next problem is as follows. Next problem is let u is equal to all those xy belongs to R2 such that x square plus y square not equal to 1. Show that U is open in R2. So in this problem, what you need to show is that there is, I mean, so if the of the portions, the circle complement is open in R2. This is what you need to show. Now think about it, how to show this. So for that, what you need to do, I mean, okay, first of all, let me tell you this problem can be solved in two different ways. Firstly, it can be shown that U complement is open in R2. Sorry, U complement is closed in R2. That will tell that U is open in R2. And another way will be to show that U is open in R2 by directly actually finding a ball around that point. Okay. Now, first, please think about it by yourself for a few seconds. Let me know. Do you have any understanding how to proceed the problem? Or first, let me know. Are you actually getting that point? How to get some kind of ball around any point? The point is that you need to find some open ball of some radius around that point, which will lie inside the region itself, right? So please let me know, are everyone understanding how we can get some ball around any chosen point of some very small radius?
Excuse me.
Yeah, tell me.
The U is the some regions except the unit circle. That is
Correct.
true.
Sorry, in between your voice break. Can you please repeat again?
The U is the region of R2 except
Yes.
the unit circle. Except unit circle.
Correct.
And we have to show that U is a open in Rn.
Right. Correct.
Okay.
So for that, what you need to do, you need to take any point from the region and you need to find some kind of open ball around that point in such a way that that open ball entirely lies inside the region capital U. I mean, so it should not intersect the circle, right? So first, let me know. First, tell me, it is possible or not to do.
It is possible we can do the two cases. One is
Huh.
the outside the unit circle, and another is the outside the unit circle automatically gets the open actually because it is infinitely extendable. But
Correct.
inner inner part is the has no the boundary part, so it is only contains the interior part. That's why it is open.
Sorry, can you please repeat your argument again?
The interior part
Hmm.
of the unit circle, we have the mm, only if we consider any ball or any disc like thing, then
Hmm.
it does not contain the boundary as a unit circle. That's why
Hmm.
we can only consider something as a interior of the thing
Yes.
as a open.
Okay, yes. And what about outside portion?
Outside person is automatically, it is trivial na.
Correct. Right, it is trivial. Good observation. So that I understand. So now tell me how to make it mathematical.
That thing I can't do actually.
No, no, I mean whatever you said, that is already mathematical. So if the point is inside the circle, so you need to choose some radius which is smaller than the point and the distance from the point to the perimeter, right? You need to
Hmm.
consider radius which is less than that, and that ball will lie entirely into the circle. And if that point lies outside, then you can choose some point. Sorry, a point lies outside, then you can choose a small ball that will lies outside the circle itself. So it will do the job. Correct.
Hmm.
So this is one way of showing something open. Now the point is that for a simple kind of equation, this kind of so showing openness seems to be complicated somehow. Okay, so now instead of directly showing use open in R2, try to show U complement is open in R. Sorry, U complement is closed in R2. Try to show this first. I mean, U complement closed in R2 means that you need to show the circle is open in R2, right? Correct.
Hmm.
So tell me first, how to show something is closed? I mean, I understand that there is some definition, but first tell me, other than definition, what are the ways one can show some set is closed, other than using the definition?
Other than that, I have intuitive understanding. For example, if
Hmm.
some set has its boundary included, then it is
Yes,
closed.
correct. That's right. That I understand. But mathematically, how to show something is closed other than the definition of closeness?
If we consider any ball and it another ball or in real line neighborhood, and
Hmm.
this neighborhood goes some portion of the neighborhood goes outside of the region, uh, then we can say that uh, it is a close. There is a
Correct.
boundary. There is a boundary. Actually, this means that it
Correct.
con it
Correct.
contains boundary.
Correct. Other than this,
Other than this,
any sequential criteria do you know regarding closeness? Okay, first tell me you have defined an real analysis course, correct?
I did real analysis.
So in real analysis, so there are two definition. It contains all the limit points it is closed and the definition you have just said. These are the two definitions you have seen in real analysis, correct?
Hmm.
And in real analysis, have you not seen any definition, any criteria of closeness as a sequential approach?
I do not recall because it is very long before I did this.
Okay, okay. So I hope you can recall that the criteria is as follows. Suppose, well, let me write it down for 1 minute. One minute. One minute. Huh. So so it is as follows. Suppose if closed if and only if for any sequence xn in f, this sequence xn in f, if xn goes to x, then x then x will also be a point inside f. So this tells that if there is some sequence inside capital F such that a sequence converges to little x, then the point of convergence will also belongs to f. So yeah, so this is the sequential criteria of closeness. Now can you recall? Are you able to recall this criteria?
Yes,
Okay. Okay. Now using this criteria, now point is that in matrix the same thing holds. Okay. The same proof. Okay. Okay. So now using this criteria, can you try to show that the circle is closed in R2? So for that, what you need to do, you need to consider sequence xn comma yn, right? Xn comma yn, where into the sequence will lie in S1, and we need to assume that the sequence xn comma y converges to x comma y. Now you need to show that x comma y, this point will belongs to S1. Do you understand what to prove actually? Do you understand?
yes.
Yes. Now tell me how you proceed. So you have some sequence xn comma yn inside R2 and such that the sequence lies in entirely inside S1 circle such that the sequence converges to the point x comma y. Now you need to show that the point x comma y lies on the circle. Now tell me what to do.
S1 is the one one circle.
Yeah, S1 is a circle. Correct.
Yes,
S1 is
yes.
x comma y such that x square plus y square equal to 1. The each point with the sequence also lies in a circle. You need to show that the point itself lies on a circle. Think about it, it will not difficult. Just you have already one information that x comma y, xn comma y, and that sequence converges to the point x comma y. So now what you will do?
Xn and Yn belongs to S1, and
Yes,
x comma xn and yn converges to the x comma y.
correct,
That is the our assumption or thing.
correct.
Then, uh, as for n can be any number, any
It is,
natural number.
it is a sequence. X and Y coming is a sequence. Yeah, n can be big.
So 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 its limit point also contained in S1, because
So that is the thing we need to show, right? Sequence the limit of a sequence is nothing but the limit point of the sequence, correct? So this is the thing we are trying to show, correct? So firstly, thing is that since the sequence xn comma yn converges to xy, this implies that 1 minute. This implies that the sequence xn goes to x and the sequence yn goes to y. Okay. Have you seen this before? Please tell me, have you seen this before?
yes,
Yeah. So now you have sequence x and y and separately converts the x and y. Now what? How to show that the point x comma y will lie on the circle? Remember that you have the already observation that the each point of the sequence xn comma yn lies on the circle. Now using this you need to only show that the point x comma y lies on the circle. What to do?
we square it and add it. The,
So then okay, xn square plus yn square goes to x square plus y square. Correct. Then
then we use the relation that it For circle, it will be 1 x square plus 1 y square equal to 1. So xn square plus yn square equal to converges to the 1 to circle.
No, no, I mean the point xn comma yn, it is already lying on the circle, correct?
Mm-hmm.
So in that case, this xn is square plus yn is square, this is already equal to 1, correct?
Mm.
So this tells what? This tells that the point x is, I mean the x square plus y square equal to 1, correct?
Mm.
So this is what we are trying to show, right?
Yes.
So now tell me, do you understand the whole thing? So
Yes.
other than open wall, only we other than showing openness, we here proved that its complement, that is nothing but the circle, unit circle, is closed. So for that, what we have done, we choose a sequence x and y for the unit circle. Okay, and assume that the sequence x comma y and goes to some point x comma y. Then we are showing that the point x comma y is lie on the unit circle. So now for that, what we are doing, since the sequence xn comma yn goes to x comma y, so this implies that xn goes to x and yn goes to y. So this tells that xn square plus this tells that xn square plus yn square goes to x square plus y square. And now this thing is equal to 1. So this tells that x square plus y square equal to 1. So this
Mm.
is the thing. You understand?
Yes.
Okay. So now, so this is another way of showing something is open. Okay. And in usually showing something is closed is easier than showing something is open. Okay. So now, mm, now go to the next problem. Let A be a finite set in metric space.
It is not visible.
Oh, sorry. 1 minute. Let me write it down again. So let A be any finite set in the metric space xt. Show that A is closed. So this question is that suppose that you have some finite set in matrix xt, you need to show that A is closed. Okay. So for that, what do you need to do? I mean, yeah. For that, what do you need to do? Think about it. You can directly show something is closed, or else you can show that its complement x minus a is an open set. Okay, now observe that a is a finite set. So first think about x minus a is open. How it is it possible that x minus a is open? First try to visualize, try to think about it, and then let me know as I'll wait. Please try to think by yourself first.
So we can make as A set is the uh,
Hmm.
A set is the finite. We can make and take a sequence on the set and mm, so that this is bounded and That's why bounded.
Okay, I understand. But one thing is that sequential criteria is helpful only in the situation where you can directly apply the limit over some equation, like the previous problem. Okay,
Mm,
always it is not possible to use the sequential. I mean, you can use that is okay, but that will make the things very difficult. So,
mm,
particularly in this situation, you need to show that a complement is open. Okay. So first, so you can now think about a complement and now choose any point. Now try to observe or visualize that around that point you can get at least one open ball which does not contain any points from the set capital A. Do you understand what to do or what is needed to be shown?
mm.
There is some finite set and you need to consider look into the complement of that. Choose
Okay.
any point in the complement of that,
Uh,
and now around that point you need to visualize that around that point you can get some open ball around that point which does not contain any of the points from the finite set. First try to understand that it is possible to do. I mean, try to visualize.
okay. Does not con possible actually.
No, it is possible to get some open ball which does not contain any finite point from the finite set. Are you getting any kind of intuition?
If A is the finite set and we take the complement of A, then we get some region which does not contain the boundary of the A. Okay, so that's why we can make a open ball and so that it contains all of its
Okay, okay.
interior part.
1 minute. Can you please repeat the argument?
As we know that A is a finite set in
Yes.
metric space, and then
Uh,
uh, we take the complement of A
mm,
and we have to show that this is open.
yes.
So mm, when we take the complement, we set another set we get, and that set does not contain the boundary part of the A and the interior, its interiors.
That
So
set, no, 1 minute. What does it mean that set? I mean, the point is you are choosing some point outside I mean, you are choosing some point from the complement, right?
yes, complement.
Yes, then you need to choose some open ball which does not contain any points from the set capital A, correct?
Yes, yes.
Yeah.
So it does not. It is fully inside in the whatever we take the region of the size of the ball. So it is automatically open.
But you did not choose any point, right?
I am choosing the point from the outside of the uh,
Okay.
complement of the open ball.
Suppose call it X. Then
Suppose uh, in this problem there is a is the finite set, and we take the complement of the a and we get the x complement a. Okay,
correct, correct.
that is the our space or
Yes,
set.
correct, correct.
Then we inside this space we consider one point and take the arbitrary ball.
Arbitrary ball.
Arbitrary ball, take a point and arbitrary ball, and that ball is suppose uh, and that ball is open in the open we arbitrary open ball. Okay,
Now,
and
point is that if you consider arbitrary open ball around that point, then that ball might
hmm,
consider some points of capital, some points from capital A, right?
capital A,
Do you understand?
but we exclude.
Do you understand my point?
No, please repeat.
Yes, yes. So you are taking some point outside capital A, and
Hmm.
you need to show that it is possible to get some open ball around that point which does not contain any point from the given finite set. Correct?
Yes, yes, yes.
Now you are saying that you are choosing some arbitrary open ball around the point little x. Now, point is that since you are choosing arbitrary open ball, so it is possible that that arbitrary open ball can contain at least one element from the set capital A, correct?
Acha, arbitrary. So arbitrary term I have to eliminate.
Yes.
Yes, yes, I got it. What you are saying?
So now tell me what will be the mathematical argument? I mean, the point is not just choosing a ball. You need to show there exists a ball which satisfy that property that it will not contain any point from the chosen finite set, right? Correct.
Yes.
So
Hmm.
how to get that ball?
How to get?
Do you understand? You
Yes,
cannot
yes, I understanding. I understanding.
think about it. I mean, try to visualize it. You can draw a picture on your pen, take pen and paper, try to figure out 4 or 5 points, and then choose some point outside those. Take some point out other than those point, and try to visualize that it is possible to get a ball small enough around that point, such that
Hmm.
that ball will not contain any other point of you which you chose. Try to visualize first.
Hmm. So I have to make the mathematical argument
Yes,
for it.
correct. It is not a method. First, I try to visualize that it is possible.
Yes, it is possible. We can make um, we can uh, how to say, it is possible to show that this kind of balls are possible, not arbitrary.
Mm,
Any we can take any ball. I do not right now do not find any correct word,
mm.
but it is possible actually, so that there is some open balls at least.
So how? So what is the intuition? Tell me. There must be some intuition,
Intu-
right? So tell me the
yes,
intuition.
intuition that uh, when we consider the x complement a,
Mm.
when we that this set is already open, because
Ah,
x is something arbitrary space. Okay, It
Huh,
can
correct.
infinite extent it can happen.
Yes,
So
correct.
so we can remove the certain finite portion. We eliminate certain finite portion, that is the A. We eliminate that part and its boundary also. So um, whatever we get, it will be whatever space is driven. It actually the interior part from uh, the that is the for example circle problems. When we eliminate the circle, there is the interior part and there is the exterior part. We are in this problem only we consider the exterior part only.
Firstly, it is a finite set, correct? So
Yes,
there is nothing like bound. Circle, the circle is some kind of, it makes something bound, right? But
yes,
finite set cannot bound anything, correct? So there,
okay.
the interior exterior word does not make any kind of sense, correct?
Hmm.
So visualization will be as follows. Let me draw some few points first. So these are the few points, and in between we have that space capital X. Okay. Now we can consider the distances from that point to capital X. Okay. Suppose these are distances d1, d2, d3, d4, d5. Okay. And choose some real number r which is less than the minimum of the distances d1, d2, d3, d4. It is always possible to do, correct? It is always possible to choose such a real number, correct?
Yes,
Now, 1 minute. Um, Now, if we consider, huh, now if we consider an open ball of radius r, so if we consider an open ball of radius r around that x, that ball does not contain any of these points, call it y1, y2, y3, y4, y5. So that ball does not contain any of the point y1, y2, y3, y4, y5. Correct?
yes,
Yeah. So the same process we can apply for arbitrary finite set. We can consider the distance from the point to each of these points, and we can take the minimum of the distances. And if we choose an uh, open ball of some radius, which is the minimum of the distance from that point to all possible finite points, and then the open ball around that point, that open ball will not contain any point from the chosen finite set. Correct?
yes.
So now do you understand the full argument?
Yes,
If you have any doubt, please ask me, okay?
yes, yes,
No need to hesitate. Okay. So this problem is clear to you?
yes.
Okay. And what about others? If is are you understanding? I shall wait for a few minutes. If I don't get any questions from you, then I shall go for the next problem. Okay. Okay, Rahul. Okay, so now there is no question I'm getting. So, okay, so the next question is as follows. Um, Let XD be our discrete metric space. Find all, sorry, closed sets in X. Suppose XD be a discrete metric space. Now find all closed sets in X. So observe that in the previous problem, what we have in the previous problem, sorry, in the first problem, we have shown what are the possible open sets in a discrete metric space, right? And in this problem, we are asking that what are the possible closed sets in a discrete metric space, okay? So now, firstly, tell me how to approach this problem. Look, okay, so firstly, observe that we have some information. We have the information regarding the list of open subsets of the discrete metric. Now, from that, what is the easiest way to get the list of closed subsets of discrete metric? Anybody? We have already information regarding the open subsets. Now, how to tell regarding closed subsets of this?
So any singleton set is open or closed in so that argument can be followed similarly.
I mean, okay, you can follow, but firstly observe that what is the closed set? I mean, by definition, I mean, so closed sets is a complement of open sets, right? And you have
Yes,
already list of all possible open sets are discriminatory. So from that, how you can get the all list of all possible closed set? See, closed set is complement of open sets, and you have already a list of all possible open sets. So how you can get the closed set now?
but by taking the complement.
Ah, yeah, obviously. And what are the all possible open sets? All possible open sets, nothing but the all possible subsets, correct? That we have
Yes,
seen. So what are the all possible closed set? You need to consider all possible complements of all possible subsets. So that will be all that will always be all possible subsets of capital X, correct? You understand?
yes.
Yeah, so that is the argument. So just by writing one line, all possible any subset of X will be closed. Okay. So does everybody understand this problem? If not, please let me know. In the meantime, let me write down the next question. Okay, I hope this problem is clear to everybody. So now let's move for the next problem. The next problem is that suppose you have given some set x equal to R2. Okay. Now with some usual metric, Now, now the set capital A is equal to x-axis union y-axis. Now we need to show that capital A is closed in R2. So what to do? So here for this, just for giving hint, for in order to show closeness, you can do two way. Either directly show closed by using sequential criteria, or you can consider the complement of capital A inside R2, and then you can show that the complement of capital is open. So first try to do it yourself, or then I will discuss. I shall be back after a few minutes. After 2 3 minutes, I shall be back. Okay. Please try to solve it by yourself first. So are you able to think how to at least approach this problem, or at least how do you able to visualize how to approach it? I don't asking for mathematical argument, asking at least for visualization.
We can take any sequence,
Okay. Okay then.
that is sequence of and yn.
Sequence of xn and yn. One minute. Okay, in capital A, and suppose assuming the sequence goes to x, y, then you need to show
Uh,
that x,
like
y
come out.
are nesting. Your voice is breaking. Can you please repeat?
So then xn comma 0 is in the sequence and it has limit point x comma 0.
Okay, then.
And similarly, 0 comma yn is also in the sequence which converges to 0 comma y. So
Well,
both are in the
but there might be points inside the sequence which either one coordinate is, I mean the point is that some points of the sequence are in the x-axis and some point of the same sequence are in the y-axis. That is always possible. That might be possible, right?
yes sir. X
Yeah. So,
comma 0, that is xn comma 0 is in x axis and 0 comma yn is in y axis.
huh, but uh, but xn comma 0, when you are saying that xn comma 0 is a single separate sequence and yn comma 0 is another separate sequence, correct? You are constantly like that, right?
Yes sir, it's sequence.
But one sequence can have different term of like one sequence can have different terms from x-axis and y-axis itself, correct?
Yes, but both have a limit x comma 0 or y 0 comma y respectively.
Yeah, correct. Okay. Okay then.
So since x comma 0 is in x axis, it is in A. 0 comma
Yeah.
y is in y axis, it is in A.
Yes, then.
Uh,
Okay, I understand your point.
so
I understand
they
your point. Firstly, I understand your point. Okay, that's correct. But firstly, tell me that set capital A, is it possible to write the set capital given set capital A as an 1 minute as an closed form of the equation? Is it possible to write this capital A as some if so for some function f such that f of xy is equal to 0? Is it possible to write this at capital F is equal to all those xy such that f of xy equal to 0? First try
so
to think.
sorry, please write and show, sir.
Yeah, okay. Is it possible to write the set capital A as the zero set of some function? I mean, is it possible to write the set capital A containing all those xy such that f of xy is equal to 0 for some function f in two variables? Is it possible?
Yes, maybe on for the points of x axis, we have f of x comma 0 is equal to 0.
No, 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 no.
Okay.
What I'm saying that is it possible to write the set capital A as all those points x comma y such that f of x comma y is equal to 0 for some function
Yes, sir,
f?
it's possible.
Yeah, which function?
Maybe we can define the function as xy.
Ah, yes, that's what I'm asking. So now it's a closed form, correct? I mean, you can write the equation. So now
Yes,
whatever the argument you were saying xn comma yn, now you can directly put that argument xn yn equal to 0 and you can now consider limit here. You can consider limit here and that will give xy equal to 0. So that tells that x comma y belongs to capital A. You understand?
yes, sir.
That's good. So, okay. So now, okay. Now the next question. Okay, what about others? Do others understand this problem? Let me write on next question. In the meantime, if you have any doubt for this question itself, please ask me. Okay. So the next question is, where is the question?
Sir, can you repeat the solution of the previous question
Yeah, sure,
shortly,
sure, sure.
briefly?
Yeah, yeah, sure. So the set capital A is nothing but the union of x-axis and y-axis. Okay, 1 minute, please. Yeah. So this is the union of x-axis and y-axis. Okay. So this can be written as x, all those points x, y, such that x multiplied by y equal to 0, right? Now we need to show that the set capital A is closed in R2. So this can be done in two ways. Firstly, directly showing closeness by using sequential criteria, and another is direct one can consider by taking the complement of this. 1 minute. Uh, Another way showing is one can consider by taking the complement of this R2 and by showing that complement is open in R2. Okay, that is one possible another way. And here we have used the sequential approach. That is, we choose some sequence x and y inside capital M and assume that this sequence converges to point x comma y. And now we want to show that this x comma y will belongs to capital A. This is what we want to show. Correct. So for that, what we need to show? We need to show that x multiplied by y equal to 0. Right? This is what we need to show. Am I right?
Yes.
Yeah. So now for this, we need to use the fact that the sequence x n comma y n lies inside capital M. Since x n comma y n belongs to capital A, so this tells that the multiplication x n comma y n equal to 0. Right? Now since x n comma y n goes to x comma y, so this tells that xn goes to x and yn goes to y. Correct? So now we can apply the limit inside the sequence x and y equal to 0, and applying limit will give xy equal to 0. So this tells the point x comma y belongs to capital A. So this is the argument. Do you understand?
Yes.
Yeah. Okay. So okay. Now so the next question is as follows. Let A belongs to X, be a point in metric space
It is
X.
not visible.
Oh, sorry. Yeah. Suppose A belongs to X be a point in metric space X, and suppose R greater than 0. Show that the set of X belongs to X such that DAX is equal to R is closed in X. So basically what this is, so this is what you're asking is that 1 minute. Why it is not going up? 1 minute, please. Okay. So so we need to show that all those x belongs to x are dx equal to r, and this said you need to closed. We need to show that this is closed. So for that, so basically this is nothing but saying that if we consider the open ball of closed ball of I mean if you consider circle of radius r around that point given capital around the point little a, then that will be closed in x. The similarly which you have observed in the circle situation, the real line case. Okay, the same thing whole metric space. Now try to show that this is indeed true in the metric space. Plus try to do it first. Try to solve it by yourself first. Okay. You can do two ways. Either you can use sequential approach, or you can consider the open. You can consider the complement and try to show that this is open inside capital X. Try to do it by yourself, or else I shall do. First, try to do it by yourself.
I have some argument.
Yeah, tell me.
That is there is some ball actually in the metric space that has radius r.
Ah, yes.
So we can assume that x equal to we assume some point on the ball x
Hmm.
equal to x naught and consider a open ball, any open ball.
Okay.
Okay,
Mm-hmm.
and so we can easily see that some part of, not all of its interior lie, this ball is not lying in uh, the as this this uh, sorry to say,
Yeah,
this
no problem.
region,
Okay.
this ball actually, this circle actually, circle or something,
Mm-hmm.
d equal to a x equal to r, this does not satisfy.
Mm,
There is a
okay.
some out region
Okay.
content, so
Uh-huh.
that's why it is a close. If actually there is a two balls, so it is harder to say which ball is which. I do not.
Okay.
Suppose
Can you please repeat the argument once?
suppose whatever we ball consider, suppose we call it b1.
So you are showing that the set is open, the complement is open, right?
Complement is open.
Mm, mm. Yeah. Okay. Continue.
Suppose this is the ball b1, and suppose particular in b1 this actually, no, not this is not a ball, this is uh, d time d sphere,
Hmm.
actually, by n sphere,
Hmm.
and we consider on site, uh, on the sphere we contain, we assume some point and we consider a open ball around this uh, around this point, and we easily see that this ball is not, this ball is the, there is some reason in the this open ball which does
Hmm.
not contain in the uh, unit in sphere. That's why it is close.
Um. Okay. How to show that it does not contain any sphere? I mean that ball.
Because this is the, suppose in two dimension it is x square plus y square equal to 1, and
Hmm.
we assume that we assume some point in this uh, point, and so any small circle and any intuitively I am talking about very intuitive,
Uh-huh. Yes. Yes.
and consider we, there is a circle and we contain, we allocate some point outside the circumference or perimeter, and
Hmm.
circumference, and then we easily see that
Hmm.
all of its part, all of its interior does not lie in the this circle.
Okay.
That's
Huh.
why some part will be interior, some part will be in outside, so that is not close
No,
actually.
no.
Open.
You need to show that ball you are considering the point. That ball does not intersect the circle. If some part of the ball is inside the circle and some part of the ball outside the circle, then
Hmm.
that ball actually intersects the circle, correct? But
Yes,
that is
intersection.
but uh, that is not that is not what we want. We want some ball which does not contain any point from the circle, correct? Do you understand?
No, please repeat.
We only want some ball which does not contain any part from the circle. Understand? I mean, the
Okay.
intersection has to be empty, we want. Okay.
Hmm.
Yeah. Now try to figure out how to do. I mean, intuitively, I mean, at least try to figure out intuitively. Then we can go for mathematical argument.
Open is Okay, I am thinking.
Yeah, please. Yeah, Mr. Rahul, tell me.
So suppose we take, I mean, suppose I name the set as S and the complement does not satisfy the condition d of ax is not equal to r, maybe.
Mm.
Then can we approach in a way that d of a comma x is greater than or otherwise d of a comma x is less than r?
Ha, yeah, correct.
Then choosing a suitable epsilon for that both each case,
Mm.
we can say that d of a comma x is greater than r and it is less than r.
Sorry, choosing epsilon, then what you said?
Choosing a suitable epsilon for d of a comma x
Mm.
greater than r,
Mm-hmm.
we get the ball lies inside the complement,
Mm-hmm.
and choosing a specific, just a second, choosing a specific epsilon for the
Mm.
condition d of a comma x less than
Mm.
r, we
Yes,
will get again the ball is contained in the complement.
correct, correct.
So from this, we can say that there exists an open ball around that
Right,
particular
absolutely.
point.
Yes, yes, correct. Very, very, very much correct. Very much correct. Yeah, absolutely correct.
Okay. So the complement is open and the set S is closed.
Correct. Very, very good, very good. So yeah, so what Rahul said is absolutely correct.
So, but I
So
have a doubt
yeah,
that
please.
what epsilon can we choose here to prove that condition?
Okay. So 1 minute. So 1 minute. So now you have some point A, and mm, you are considering circle around the point A. Okay. Now now if you choose some point little x inside the circle, okay, then you can consider the distance, and you can consider any radius which is less than the distance. Then you consider the ball around that point, then that ball will lie inside the circle fully, correct? Right? How you are choosing the radius is nothing but, first you are considering the 1 minute. How you are choosing the radius, nothing but first you are considering the distance from this point x to the perimeter, and then you are considering the minimum of the distances. Sorry, you are considering the distance which is less than some radius which is less than the distance from the x to perimeter, and then you are considering the open ball around that point x. Then that ball cannot intersect the circle, correct?
Yes,
Yeah. So inside, so it's for interior situation, we can choose the ball like this. And if the point is outside, then of course we can um, okay. So if the point is outside, then we can consider the open ball, um, which is less than the distance from y to the circle, and then we can consider the ball around the point y, and this will also not intersect the ball of the that given open ball of radius r, correct? Sorry, the given circle radius r.
yes, sir.
Yeah. So now, now you do understand the argument. If any doubt, please ask me. Or else we can go for the next problem. Okay, let's go for the next problem. Um, 1 minute. So for any subset A of the matrix XT, we can define interior of A. It is known as the interior A. This one to be all those X belongs to A such that um, mm, 1 minute, such that X is an interior point of A. Now show that interior A is largest open set containing. So what is the statement? Suppose A subset of X comma D. Define A interior to be all those X inside capital. So the X is an interior point of A. Now show that interior of capital is the largest open set contained in A. So for just for your confirmation, what does your interior point? Interior point is a point is an interior point if there is an open ball around that point which lies entirely inside the set capital A, that will be interior point. Okay, now show that A interior is the largest open set contained in A. First try to think about how it is possible. Okay, so firstly try to show the hint is as follows. First hint is show that A interior is open. This is the first hint is that show that A interior is open. Yeah, Rahul, tell me. Yeah, Rahul, tell me.
Uh,
Yeah.
so by definition, we have interior of A consists all points of A, that is
Yes.
all interior points of A.
Yes.
Then we have to show any set of, I mean, any open set of A. Say for example, X.
No,
Uh,
firstly tell me, firstly show that A interior is open.
oh, okay, okay, sir. Then consider any point X in interior of A.
Okay, 1 minute.
Since X is the interior point of A, that exists an open ball
Hmm.
uh, with center as X contained in A, such that it is also contained in interior of A.
No, that is what we need to show, right? X belongs to interior of A. So this implies X is there exists an open ball around X which lies inside A. Now we need to somehow get some kind of open ball inside interior
Such
of
that
A, correct?
X belongs to B of X comma R, that is open ball.
Uh,
So for every point X, we can find an open ball that is entirely contained in interior A.
No, that is what we need to show. How to show that open ball is contained in entirely interior of A. That is what I'm asking, correct?
Oh, yes, sir, yes, sir.
Yeah, yeah. Please think. Please think about and let me know. Do you understand what I'm asking actually? You need to show that open
I,
ball lies inside interior, but how to show that? That is what we need to show, right? So please try to think about. It is not difficult, it is easy, but you just try to think that it is the case actually.
sir, can you show a bit of question?
A bit of question
Can you
means
scroll to question? Just a
haha.
second.
Yeah, yeah. This one, right? Oh, yeah. Okay, sorry. 1 minute. Now, okay.
Okay. So then we have to prove every point in the open ball is also interior of A. Uh,
Yes. Wow.
um,
Yes, of course. How to prove that? Whatever said is correct only, but how to prove that?
then by definition, let us take any point. Sorry,
Yes.
sorry. Let us take any point y, and then by definition, let us apply that x minus y is less than r. Distance between x and y is less than r.
Hmm.
Then, if we choose epsilon, a suitable epsilon for that, then we can apply the condition for that particular point. That is, there exists a open ball for that particular point,
Okay,
and that is
so
contained.
now so first um one show that this bx comma r subset of a interior. So this is what first try to show. Okay, first try to observe this is the case indeed. Think about it. Okay, this is what you need to show. So first think about how to show this. Why when it is possible it is true in the first place.
Sir, suppose from the set A naught, we
Hmm.
can assume we take any point, and this point, around this point we take the B ball and
Uh,
with radius r, and this gives the all, and it's all point containing the A naught, because uh, all the points of A naughts are interior point. By definition of the definition, applying the definition of interior points, we can easily see that B naught B x comma r belong subset of a naught.
Right. Correct. We can say like that. Yeah. Mm. Hmm. Correct. Right. So, okay. So, Rahul, do you understand argument now?
Oh, yes, sir.
Yeah. Yeah. Okay. Okay. So now, 1 minute. Hmm. So now we have shown that Bx comma subset A interior. So this implies what? This implies that A interior is open, right? So this is first part, okay, right? Now we need to show that A interior is the largest open set contained in capital A. Now we have already shown A interior is open. We need to show it is the largest open. Okay. So second observation is that show that firstly show that if U subset of X is open, then U interior is equal to U. Okay. Oh, sorry. Huh. Show that if U is subset of X open, then show that U interior is equal to U. I mean, this is the part of the given question itself. For that, this is the second part. We need to show that some set is an open, then its interior is nothing but the set itself. So how to do that? I mean, think about it. It's very obvious. Just think about it. That it is obvious.
I have some intuitive idea.
Yes.
You are saying that U is a open in the open set and which will is the subset of X.
Correct.
Then U not equal to U.
Correct.
Okay. So that
Yes.
is the thing we have to show. So
Right.
so if we have a open set, it means that we have all the interior points, and
Mm.
mm, we ex- mm, we exclude the boundary of the
No, for
mm,
first of all, forget a boundary. There is no boundary coming to the picture. Correct. You only need to
yes.
show U interior is equal to U, right? Now try to
uh,
show that.
so by the definition of the open set contains the by the use of the open set, we can easily see that it is the case. The open set definition is that consider suppose there is a set and assumes any point inside the set, and uh, um, then do the some open ball,
Hmm.
and it contains in this set, all of it containing this set that you said.
Correct. Right. Absolutely. So whatever you said, that means that if you choose any point from U, then of course there is an open ball BXR subset of U. And of course, and this is quite obvious that this open ball actually subset of U interior. This is what you said, correct? Yes or no?
Yes.
Yeah, okay. So this tells that for an open set, U interior is equal to U. Okay. Now, go to the question. So what we need to show? So there we need to show A interior is the largest open set contained in A. Okay. Now we all have the recipe for showing this. Now what you need to do? You need to check that if any it is the largest. So if any open set is contained in A, then need to show that that open set is contained inside A interior. That is, we need to show, that is to show, oh shit, 1 minute. That is to show, 1 minute. The software was not working. What happened? 1 minute, please. Huh. That is to show if U subset of A is open, then U subset of A interior, right? So this is what we need to show, correct? So this will tell the A interior is the largest open set contained in capital A. Am I right?
Yes.
Yeah. Now prove this. Whatever we have seen till now, using that only it is possible. Try to think and tell me that whether you are able to understand, able to solve this or not. Okay, let's try.
So since U is open for any point in U, there exists an open ball contained in U.
Okay, X belongs to U, so B X R subset of U.
U,
Okay, yes,
which is ultimately contained in A. That
yes,
means
yes,
X is interior point of A.
yes, correct, very good.
Then X belongs to interior A.
Right, right, correct, absolutely correct. So this tells that, okay, so this tells that A into the largest opposite contained in capital A. So this is the argument. Does everyone understand the argument? Does all of
Yeah.
you understand the argument? Okay. So now let's proceed for the next question. One minute. Okay. Now the next question is as follows. So, so let U subset of the matrix X comma D show that U is open if and only if U is arbitrary union of open walls. Some subset U in a matrix is open if and only if U is arbitrary union of open walls. Try to think about how to do that. It is not difficult. Do you understand what is needed to be proved? Do you understand what is needed to be proved? So you need to find, you need to show that union, any open set is a union of open balls. So, I mean, okay. So look, so firstly, it is, look, so since it is an open set, so around any point of that set, you can get some open ball which lies entirely inside the set capital U. Am I right? Am I right?
Yes.
Wait. So, so each point has some open ball lies inside you. So if you choose all possible point, and for each point you are getting some open balls. Now, if you take the and the open balls lies inside you. So if you take the union of all those open balls, so you will get the set capital U itself, correct? At least intuitively. Am I right? What I'm trying to say is the following. So this is some U. Sorry, it is not a circle anyway. This is it. And now, for each point, you are choosing some balls. For each point, you are choosing those balls. Now, if you are taking the union, that those union will be nothing but the full capital U, right? At least intuitively.
Yes.
Yeah. So now how to prove that? So only what we need to show? We need to show if we take open balls around each point, then the union of all those open balls will be nothing but the whole of U. This is what we need to show, right? So how you can prove that? Mathematical, of course. Try to think. I stop after 2 minutes. So how to do that? Okay. So it is quite obvious, but proof is quite tricky. So let me write it down for you. So so you are taking x belongs to, sorry, you are taking x belongs to you. So there exists some rx greater than 0 such that x belongs to bxrx subset of u. Okay. Now you are considering this union, this subset of union of x belongs to u, bxrx subset of u. So and this left side will nothing but this is equal to u. So this tells that, so this tells that union of x belongs to u, bx radius x, this is equal to whole of u. So this is it. So do you understand? Do you understand the trick? Do you understand the trick? Please let me know. Do you understand the trick?
Yes.
Hmm. Okay. Now, so this tells that any open set is union of n balls. Okay. So this is one thing. So now, okay. Now there is one more question, namely, so I am going to the next question. Is that one minute? The question is, what are the metric spaces in which only open sets are x and phi? What are the metric spaces in which only open sets are x and phi? So we have uh yeah, yeah, okay. So mm, mm, yeah, try to think. So what are the metric in which the open sets are x and phi? Let's try to visualize from using definition only. No, trivial means all trivial. So Rahul, what you ask, the trivial means all sets are all subsets are open. Okay, that is trivial. But here, the what are the metrics? Only open sets are x and phi. Try to think. Okay, so let me write it down the hint. Uh, Show that such metric space can contain only one point. So all if only open sets are X, then you show that such matrix only contain only one point. So what does this mean? You need to show that if such a matrix will contain more than one point, now then you need to find some open set which is neither capital X or nor the empty set. How you can do that? I mean, it is easy. Please try to visualize it. Please try to. I shall give back after a few minutes. Uh, Hello. Yeah. Yeah. So now tell me, are you able to understand? Okay. So Rahul raised hand. Okay. So tell me, so are you able to solve this?
So here we have to prove the metric space contains only one point. Then can we assume that there are 2 points and arrive at a contradiction?
Hmm. One minute.
That is,
Ah,
say
yes,
for
yes,
example,
yes, of course. Definitely, that is what you need to do. Correct. Yeah.
oh,
Now.
okay. Then say for example, let me consider two distinct points A B in the metric space
Okay.
X.
Okay. Mm-hmm.
Then by definition, we can have an open ball
Mm-hmm.
containing A,
Mm-hmm.
and since the open ball contains A, the
Mm-hmm.
open ball is not equal to phi, that is null set.
Mm-hmm.
Then the open ball is not equal to the metric space X,
Mm-hmm.
since if we take any other point, it will not it may not satisfy the criteria.
Mm-hmm. Okay.
So the open ball containing A is neither the entire metric space or phi. So it leads to the contradiction that the only open sets are X and phi.
Correct. Correct. Very good. Very good. Very good. Right. Correct. Yeah, that's good. So whatever Rahul said, the argument is absolutely correct. Does everyone understand his argument? Does others understand the argument? Okay. Okay. So since nobody is saying, so I can assume safely that everyone understand argument. So it's now 9. So you will stop here for today. If you have any doubt, you can ask me in the email or you can ask me in the next live session. Okay. So we shall meet on upcoming Friday from 7 to 9 p.m. in the same Google Meet link. Okay. So I'm ending the session. Yeah, that email is in NPTL. There is an announcement. You can post your question in the announcement tab. I will get your email. Okay. Understand? Okay. Okay. Thanks, Raul, for the confirmation. Okay, then I'm leaving the call.